Okay, in this video we're going to go over the 6.4 notes, and they cover areas in the xy plane. So there are two big topics here. One is the area between two curves, and the other is the area bounded by curves. Now, in both of these cases, you need to put these graphs in your graphing calculator and look at them, because their position relative to one another is critically important in your problem setup. If you're not doing that, there's a very good chance that your entire problem will be incorrect. So please, please, please make sure you graph this in your graphing calculator. Okay, topic 1 is the area between two curves, and mathematically depicted, we can say in this little yellow box, if y is f of x and it lies above y equals g of x, from x equals a to x equals b, the area of the region between f of x and g of x from x equals a to x equals b can be represented as this integration problem below. Okay, so we see a and b are the endpoints. So here's a, here's b. Here is your integrand. Look at that integrand. The integrand is the difference of those two functions. And the reason why f of x is first is because it is above g of x. Okay, so now look at this picture below. And you can't see all of it in this shot, so let's go on to the next page and I'll show you the whole picture. And then we'll talk about what we are seeing. Okay, here is the best picture, and they told us that the function f of x lies above the function g of x. So that means that in the interval from a to b, every y value of g of x is below the y value of f of x. Okay, f of x is above throughout that whole interval. Here is the area between the two curves. This is what we are looking for. That's going to be an area, and it's going to be an integration, because that's what integration is. So the endpoints are a and b. And looking at this picture, I would take the f of x, and I would subtract away g of x, and then I would have the dx right there. So that's the shortened view of that problem. Things to think about. Okay, if you are given two functions, you must first determine what this looks like. So how are these functions positioned graphically? Once you see them, make sure you're identifying them correctly, and then you'll know that you're going to subtract the lower curve from the upper curve. So that's what this think about is. This says you may simplify your integrand before finding the antiderivative. I would say that's a must. Don't start working until you have the simplest integrand possible. And it's the simplest algebraically correct integrand possible. Okay, you are given your a and b in this situation where you have the area between two curves, and therefore the problem is going to use the FTC, which is the fundamental theorem of calculus. Okay, let's go on to the next page. Okay, here is an example of finding the area between two curves where you have actual functions, not just an f of x and a g of x. So if you're asked to find the area of the region between this curve, y equals 2x minus 4x plus 6, and this curve, y equals negative x squared plus 2x plus 1, from these endpoints, your first step is to put it in your graphing calculator and look at it. This is what it looks like. So it just so happens that the first function ends up being the top function. Do not assume that that's going to happen. Assuming that is very, very foolish. So please, please, please graph these functions and look at them. So where is the area that we are trying to find? Well, I see endpoints down here of 1 and 2, and I see the curves. So right here where I'm cross-hatching, all here is the area. So that's going to be the area in between the two curves. That's what our goal is. When we solve this fundamental theory of calculus problem, we will get a number. That number will be the area. Okay, so let's now set this up. Okay, so we're going to have our integrand symbol. We're going to go from 1 to 2, and the function that comes first is going to be 2x squared minus 4x plus 6. Put this in parentheses. That's your first function. Here comes your second function, also in parentheses. This is to ensure that you distribute your negatives correctly. So the second function, which is the bottom function, is going to be negative x squared plus 2x plus 1. All right. Because these are all written in terms of x, I'm going to put dx at the end. Now, let's see if we can clean this up. So we're not doing the integration yet. I'm going to keep my little symbol going. And now let's remove the parentheses correctly. Okay, there's no danger removing the first set of parentheses. You just write what you see, and you're okay. Now, this negative has to be distributed one place, two places, three places. Don't miss any of these. Okay, negative times negative x squared is a positive x squared. Negative times positive 2x is a negative 2x. Negative of a positive 1 is a negative 1. Okay, all of this goes behind your dx. Now, don't you dare start taking integrations at this point. You have way too many terms to keep track of. Okay, so now let's see if we can combine like terms. So you're going to delay taking this integration until everything is a nice, neat package. So here's my symbol again with the endpoints. Okay, I see a 2x squared and another x squared. Adding those together gives me 3x squared. So I'm going to check those off. They're gone. Then let's go to the linear terms, the terms that have x's in them. So negative 4x and another negative 2x gives me negative 6x. Now let's go to the constants. Positive 6, negative 1 gives me a positive 5. This is the integrand that I want to now take the antiderivative of and use the fundamental theory of calculus to get the area under the curve. Okay, so let's do our thing. We're going to write 3x, add 1 to the power, you get a 3, divide by that same value, 3's down below, minus 6x, add 1 to the power, divide by that same 2, plus the derivative was a constant, so the antiderivative must be a constant times the x variable. Okay, we're going to evaluate this. Oh, and you can say, so let me go back for a second, and you can say plus c, just to emphasize the constant of integration. But when we use the fundamental theorem of calculus, the c will drop out, but it's perfectly fine to keep it here right now. Okay, our endpoints start at 1 and go to 2. So now what we're going to do is take this value, I'm going to go on the next page, and we're going to clean this up and get an answer for my fundamental theory of calculus. So hang on until I get this organized, and you can go ahead and work on this, and we'll see if we get the same answer when I resume. Okay, here we are all tidied up. Now let's see if we can plug in a 2 for every x, and then we're going to plug in a 1 for every x, and we're going to subtract those two terms. Okay, so let's do a little cleaning up before we do that. So this is what I'm thinking. Let's reduce what we can. Okay, this 3 cancels that 3. 2 goes into 6 3 times. So let's just clean that up a little bit. So this can go away because I don't need the 3's there any longer. This can go away. Let's erase this also, and I'll make that a 3. Okay, and I really don't need this here any longer. All right, and this is gone too. So that's our nice cleaned up problem that we're now going to be working with. Okie doke. Let's change to green. Okay, so we're going to plug in a 2 wherever I have an x. So I have 2 cubed minus 3 times 2 squared plus 5 times 2 plus c. Okay, that's when I plug in the 2's. So let's see what we get there. 2 to the 3 is 8. 8 minus 3 times 4 is 12. So this is 8 minus 12 plus 10 plus c. Okay, so this is our first group of numbers. So what do I get there? I have 8 minus 12 plus 10. So that's a minus 4 plus a 10 is a 6 plus c. So this all turns into 6 plus c. Okay, so now we'll change colors again. And we'll say we're going to take this 6 plus c and subtract away. I'm going to use my parens again. Plug a 1. 1 to the third is just 1. Minus 3 x squared, so that's going to be minus 3, and then plus a 5 and plus a c. Okay, so what do we have here? 1 minus 3 is a negative 2, plus 5 gives me what? A positive 3. Okay, so I have a positive 3 here, but look what's happening. And this is also plus c, so we'll put the plus c right here. Okay, plus c. So now I have 6 plus c minus 3 plus c. The c's cancel. I get 6 minus 3. And the area right in here between 1 and 2, between these two curves, that area has a measurement of 3. Alright, so that's the area between two curves. Let's look at the bottom of the page to make sure we see what they've done, and we'll summarize it, and then we'll go on to the next topic in this section. Okay, here's our next topic, area bounded by two curves. How is this different from the previous example? Well, here we are not going to be given endpoints, but instead we must determine them by analyzing where the curves intersect. So we are looking for a region that's completely enclosed by the two curves that they give us. So an example of finding the area bounded by two curves might be stated this way. Set up the integral that gives the area bounded by the curves of y equals x squared plus 2x plus 3 and y equals 2x plus 4. Those are my two curves. First thing, put it in your graphing calculator. You may need to zoom in to see where the intersection happens. Okay, I'm going to go to the next page so we can see this a little bit clearer now that we know what we're going to do. Okay, so here's our problem. So I plug it in my graphing calculator and I can barely see that they're touching. It looks like they just completely overlap until I zoom in closer and closer so I can see a picture that looks like this. So let's use the colors that are on the graph. So this blue, so we'll say it's almost like this. This is our blue curve right here. There it is. Okay, then we have a red curve. And our red curve is a line, and that line is right there. So let's look and see where they intersect. So they intersect right here, right at this point right here, and also right here. Now I have given you the points of intersection, but you will have to do this on your graphing calculator. So you get a good picture, and then you do your intersection. You do it 2 places, and your desire is to get the x value. So I'm circling down here. Our goal is to get the area bounded, so when they cross, you can't get out of this area right here. Okay, so if you were a little mouse, you'd be stuck. This is what we want to find the area of, and we are going to use the fundamental theorem of calculus to do that. So they have given us the functions and nothing else. We put them on our graphing calculator. We're now at this point right here. I know that they intersect at x is -1 and x is +1. And I know that I have, looking away from the intersection, come in here. Do you see that there the red is above? This red has a higher y value than does the blue at the same x value. That's the case all the way along. The red is always higher on the y than is the blue. Therefore, our problem is red, so here's your red, minus blue. Notice the parentheses. Sorry. Okay, my dog is all calmed down now. So, you need to take this complicated expression and simplify it. And when you simplify it, you should get this. And I would say go ahead and try to do that. Make sure you distribute this negative to 3 places. Here, here, and here. Okay? When you do that, you should get this as your brand new perfect integrand that's easy to work with. Taking that integration, I would get x minus x cubed over 3, and then you can add the plus c, and remember you're going to run that starting with 1 and then subtracting away the value when you have a -1. So doing that, you should be getting 1 1/3. So try that now. You can stop the video and then you can resume. Okay, so I'll do that now over here. So I have 1 minus 1/3 plus c minus -1. So I have a -1 here, minus -1 cubed. That's going to be a plus 1/3, and then plus the c. So 1 minus 1/3 is 2/3, minus -1 plus 1/3 is -2/3, but it's a negative 2/3, so it's plus 2/3, which gives me 4/3, which is equivalent to 1 1/3. Okay, so that ends our 6-4 lesson. Graphing is key. Position of the graphs is key. Double check that to make sure you are doing it correctly. In the bounded, I should say, sometimes they'll tell you to look in a certain area. So let's say we're doing this problem. They might say, look at the area -2 to 2. Those are not your endpoints. That's just where you're looking to find your bounded, to find where they intersect. So do not be thrown off if they give you values to look at. They are not your endpoints. Remember that. For bounded, you have to provide your own endpoints. Okay, so that covers 6-4. That's my last official lesson. You have lots of review materials. Use all of it to your advantage. Re-listen to these videos as needed.